I will now talk about two basic rules for counting, the product and division rules. And remember that counting is all about counting the cardinality of a set. In our case, it's always finite set. We want to count the elements of that set. Now, the product and division rules apply to cases where the set can be described in terms of other sets using product or division. So the product rule says the following. If the set A, whose elements you are trying to count, can be written as the Cartesian product of n sets, each of its own cardinality, then the cardinality of A is the product of the cardinalities. We can prove this easily using induction. But think about it that you're looking at the set A. Every element in A is a tuple of n elements, the first from A1, the second from A2, the nth from AN. The number of ways you can have elements in A is the number of ways you can form such tuples, and this is the rule that we have. Okay, and this rule is very simple, yet it's very powerful, and it appears in many counting problems. Let's look at the first example here. For example, how many different DNA sequences of length 10 are there? So DNA sequences are basically strings where every position, every letter in the string can be either A, C, T, or G. Okay, and we have the length, the string is of length 10. So here I'm talking about the set A is the set of all different, actually we don't need even this, all DNA sequences of length 10. Okay, so I can then write this as, if I look at A1 as the set, not this, all possible DNA letters. Okay, in other words, this is A, C, T, G. I can write A2 to be the same, A, C, T, G. And I can write all the way to A10, it's the same, A, C, T, G. Now, if you look at A, the set A can be written as A1 times A2 all the way to A10, right? Because every sequence of length 10 can be written as a tuple of 10 letters, the first from A1, the second from A2, the third from, and so on. So now by the product rule, I know that the cardinality of A is the cardinality of A1 times the cardinality of A2 times the cardinality of A10. Now the cardinality of A1, it's simple. We have four elements in it, it's 4. The second is 4, all the way to the 10th is 4. So it's 4 to the 10th. This is the number of DNA sequences of length 10 that we can have, right? If I ask about what's the number of binary strings of length n, it's the same trick. A1 would be the set that has 0, 1. A2 will be the set that has 0, 1. All the way to AN be the set that has 0, 1. So the cardinality of the set of all binary strings of length n would be 2 times 2 times 2 all the way to n times. So we have 2 to the n as well. Okay, so this is one application of the product rule. Let's look at another example here. How many one-to-one functions from a set with n elements, how many one-to-one functions do we have from a set with m elements to a set of n elements? Okay, so we have, let's visualize it first. We have a set A here, and we have m elements in this one. Then we have set B here, and we have n elements. And we are looking at functions f that are one-to-one. Since they are one-to-one, it means that for every two different elements in A, we have to map them to two different elements in B. So the first thing we know is that n has to be greater than or equal to m, right? In other words, that if n is smaller than m, then this number is 0. We cannot have any functions that are one-to-one from a to b such that they are one-to-one, right? So now let's assume n is greater than or equal to m, so we have enough elements in B to map to. So if I look at them now, let's look at A, and let's look at A as being A1, A2, all the way to AM. So now I know that, and let me look at set A1 as the set of all elements in B that we can map A1 to. Okay, so I say, what's the cardinality of this set? A1. So how many elements, what are the possible elements I can map A1 to? Any one of the n elements. I could map A1 to B1, I can map A1 to B2, I can map A1 to Bn, right? So the cardinality of this set is n, okay? Now let me look at the second set here, A2. A2 will be all elements in B that we can map A2 to. Now notice that A1 has been mapped to some element. I cannot map A2 to that element because that will violate the one-to-one property. So if we have mapped A1 to some element in B, then the A2, I can map it to any of the n minus 1 remaining elements. So A2 will be n minus 1, right? And we repeat the same exercise now. We repeat the same exercise and we get all the way, to the cardinality of AM. And the cardinality of AM, after we have mapped A1 and A2 all the way to AM minus 1, now what we have here is that it's n minus m minus 1, right? So we have the m minus 1 elements have already been mapped. I cannot map the mth element to them. So we have n minus m minus 1. So now using the product rule, I know that the cardinality of A, it's the cardinality of A1 times the cardinality of A2 times all the way to AM. So it is n times n minus 1 all the way to n times, all the way to n minus m plus 1. So this would be the number of one-to-one functions from a set of size m to a set of size n. Okay. Again, it's very important here to notice how we are taking a task, which is counting the number of one-to-one functions from set A to set B. We are breaking it down into tasks. In this case, the task of finding all the elements we can map A1 to, and another task which is finding all the elements we can map A2 to, given that we have already mapped A1. Then the task of mapping A3, given that we have already mapped A1 and A2. As you break it down into these tasks, it makes your job much easier thinking about counting the ways you can perform a task and then using the product rule. Okay, so how many ways are there to map A1? There are n ways. How many ways are there to map A2? Given that we have already mapped A1, there are n minus 1 ways, and so on. So when it comes to counting, it's very important to think clearly about the problem, break it down into smaller tasks, reason about the number of ways you can perform each task, and then use the proper rule. In this case, it was the product rule. Okay. The second rule is the division rule. It's written here in terms of functional notation, but it's very important to think about it a little bit to see what it's saying. What this division rule is saying, if there exists an onto function from A to B, such that the number of elements in A that we map to an element in B is D. Okay, so for every D elements in A, we map them all to the same element in B. Then the cardinality of B is the cardinality of A divided by D. And again, if you visualize it, so this is what we have here, A and B. And what we are saying here is that if you take an element for every element B, what we are saying here for every element B, the cardinality of f to the -1 of B, which means the cardinality of the set of all elements in A that we map to B. So these are all the elements that we map to B. If the cardinality of this, so here this is D equals 4. So if we have another case here, other 4, all of them map to the same element B prime and so on. So every 4 map to the same element here. If you look at this, well, every 4 in A map to a single element in B. The function is onto, so every element in B has to have a source, or has to have, a source in A. But not only does it have one source, it has D sources. So if you look at this, just this diagram I showed here, if you have 3 elements in B, each one of them is going to have 4 sources. 3 times 4 is 12. This is why we say the cardinality of A, it is going to be D times the cardinality of B. Okay? And this is the division rule. When we write actually B is the cardinality of A divided by D. Okay? Now again, if you look at this, we are talking about the relationship between two sets. If there is a function, this function that relates set A and set B is where the division rule comes from. The function for the product rule was the fact that we could partition A into these sets, A1, A2, and so on, and AN, and write A, sorry, not partition, but we can write A as the Cartesian product of n sets. Then the cardinality of A is the product of the cardinalities of these n sets. Here, the division rule, we are saying, suppose you want to count set B. Think about set A that with this property, set A such that there exists an onto function from A to B, and every D elements in A map to a single element in B. Then you can use the division rule to get the cardinality of B from the cardinality of A and dividing it by D. Why do we want to do this? Because sometimes counting the elements of A can be easy, and finding that D is easy. So we can find the cardinality of B in terms of the cardinality of A and that D. And let's show one example of this here. So I want to count the number of ways I can seat n people around a circular table where 2 seatings are considered the same when everyone has the same immediate left and immediate right neighbor. So I have a circular table. Let's actually visualize it first. I have a circular table, and imagine I have 4 individuals, and let's call them by their numbers, 1, 2, 3, 4. So one way to put them is, this is 1, this is 2, this is 3, this is 4. Now, what the specification of the problem tells me that 2 seatings are considered the same when everyone has the same immediate left and immediate right neighbor. In other words, if I look at this seating here, if this is 4, and this is 1, and this is 2, and this is 3, these are the same seatings. They are equal. Because take, for example, 1 here. To the right of 1, there is 4, from one's perspective. To their right, there is individual 4, and to their left, individual 2. Look at 1 here. To their right, it's individual 4. To their left, it's individual 2. And so on. You can check 4, you can check 2, you can check 3. So these are the same. And also, this is the same. And this is the same as well. Okay. So I cannot count these as 4 different. When I'm looking at the number of ways I can seat n people around the circular table with this condition, I cannot count them as 4 different ways. So if you look at this problem here, it might be actually challenging to count and reason about this round table and so on. But if you look at this here, and you see this diagram and what I did, is that if you look at it, you're saying, okay, let me first put these 4 individuals in a row, like 1, 2, 3, 4. And these 1, 2, 3, 4, let me designate the top of the table as the first one. Then going clockwise, I will put the second, the third, and the fourth. So this is really, this here is really this one. Now, if you look at this, at the second one here, it is the 4. It is the 4, 1, 2, 3. This one is this, corresponds to this seating, right? Because the first one is at the top of the table, then going clockwise, then 1, 2, 3. Then the other one is 3, 4, 1, 2. This will be this one. And the other one is 2, 3, 4, 1. It will be this one here, right? Now, I know how to count these permutations here, because now I am asking how many ways are there to put four individuals in a row. Okay, so if I want to put 4 individuals in the row, I can put here in the first place either 1 or 2 or 3 or 4. And then here I can put any of the 4. Then for the second one, similar to how we counted the number of one-to-one functions, once I put one of these individuals in the first place, then I have 3 possibilities to put the second individual in the second. After I put these 2 there, I have 2 possibilities to put that the third individual. Then I'm left with 1. So this is 4 factorial. So there are 4 factorial ways of arranging these 4 individuals in a row. But as I'm showing in this illustration, every 4 of them account for exactly the same seating around the circular table. And this is where the division rule comes, is that my set A here has 4 factorial, which is 24 possible linear arrangement of these 4 individuals. But where set B comes into the picture, I'm saying that if this is the first one, this is the second, this is the third, this is the fourth, I'm saying that, and this seating here, this seating, suppose I count this as seating I, the first one, okay, the seating 1. So what I'm saying here is that these 4 seatings are going to correspond to that one, right? Because these 4 seatings, the linear seatings, correspond to exactly the same one. If you look at this, you are gonna get actually to the 6th seating here, and you will find that 24, 23, 22, and 21, all these 4 correspond to the same seating, which is the seating number 6 that is around a circular table. So here the D is 4. Every 4 elements in A map to exactly the same element in B. And the size of A, which we can count, is 4 factorial. Therefore, the size of B, which is the set we are interested in, the number of unique seatings around the circular table, is the size of A divided by D, which is 4 factorial divided by 4, and this gives us 3 factorial, and it is 6. Okay? So there are 6 ways of seating these people around a circular table. Now, if my question was about n people, so let me change color here. So since the question is about n people, we can do the same thing. The number of ways of seating n people in a line is n factorial. Every n here, for when we were dealing with n equal 4, we noticed that there are 4 linear assignments or linear seatings that map to exactly the same circular seating. So here in our case now it becomes D becomes equal n. So if you look at n, just rotate them. There are n ways to rotate them and give you exactly the same circular seating. Therefore, the size of B, which is the number of different ways of seating n people around the circular table, is the cardinality of A divided by D, which is n factorial, divided by n, which is n minus 1 factorial. Okay, so here again I broke the task of counting the number of seatings around the circular table into this set of tasks here, that I am looking at seating the n individual in a line. Then the second thing, I wanted to reason about how many of them correspond to exactly the same circular seating. then I got the number of the circular seatings in terms of these two quantities. The cardinality of A, which is the number of linear seatings, and the value of D, which is how many of these linear seatings map to exactly the same circular seating. And this is a nice application of the division rule.